Okay, we're going to look at tangents and normals now, an application of differentiation, and we've been looking at how tangents are related to our work on differentiation, so it's just an extension of that really. So initially I just want to have a look, I want to show you just what tangents look like as they roll along a curve. So all right, we've got a point A here on a cubic. There she goes. Now I'm going to check this tangent box, and so now I'll get the. There's nothing new about this, but you can see how I work with finding the gradient of a curve at any point is helped here by having a tangent to draw. So you can see there we've got our point at -2, and we must have a tangent read at some point in some state. Yeah, this line here, 4.05, is the gradient of the tangent there. 4.38, it gets steeper. It gets up here, it'll be pretty close to 0. If we're looking here on the equation of that line, so that's the equation of this tangent, it's pretty close to 0 there. It turns negative, so we're looking at the coefficient of x here on this line, and it turns positive again. And so if we're going to draw this, we would have x coordinates, x intercepts for the gradient function here and here, and it would start positive, so it would come through here like this, and turn through there, and do something like that. Okay, but when we're going to move into now looking at trying to find, we're going to concentrate on the gradients, on the tangents to curves at various points, but we're going to start to look at finding the equation of such a tangent. Not just tangents though. I mentioned normals as well. Let's show you what a normal is. It's the perpendicular at that point. So the normal at A is this red dotted line here, and that's the perpendicular to the tangent at that point A. So what we'll in effect end up doing is, if you remember the relationship between perpendicular lines, is that they product or multiply to -1, or their gradients do, their gradients multiply to -1. Or another way of thinking of that is that their gradients will be the negative reciprocals of each other. So if we can find out the gradient of this line here, how are we going to do that? We're going to derive this function, this cubic, and we're then going to sub in this value of x. That's going to give us the gradient of this line, isn't it? And then if we negative reciprocal that, we'll have the gradient of this line here. So we'll be able to find out the equation of those lines using our point gradient form of the line, which is y minus y1 equals m bracket x minus x1. So we'll get to all that in a minute, but I just wanted to show you what the tangent was. And the normal, which you haven't seen before, I don't think. Okay, so just to recap what we just did there, if we've got a curve like so, then if we're going to have a look at this point here, then the tangent, or the rate of change of the curve at that point, or the gradient of the curve at that point, is equal to the gradient of the tangent at that point. Okay, so that's the tangent to, this is y equals fx, the tangent to y equals fx at A. And now what we've just discovered there, something new, is that this thing here that goes through A but is perpendicular to the tangent is called the normal. Right, that is the normal to the curve y equals fx at A. Right, and what we're going to work on now is finding the equations of such lines. Okay, so what we need to do is recap or recall. Let's try that again. Recall that the equation of a line passing through a point let's call it x1, y1, with gradient m is, or has equation, so I've written that already. Recall that the equation of a line passing through a point x1, y1 with gradient m is y minus y1 equals m bracket x minus x1. Okay, that's going to be useful to us now. Let's have a look at an example. Okay, our first example's on the screen. Find the equation of the tangent to the curve y equals x cubed plus a half x plus 1. Okay, cubic function at the point where x equals 1. Okay, so whatever this cubic looks like, I don't know what it looks like, but if x equals 1 is there, 1 something, we're going to find the equation of the tangent to the curve at that point. So, what I'd like you to do is pause the video here and do as much as you can, and then come back to it. But just to give you the overall game plan, it's to be, what we're going to need to do is to find the gradient of the tangent and the point, the xy point. We've been given the x point, we need to find the y point as well, so we can put the x1, which will be 1, and the y1, which we need to find, into the equation with the gradient. Now the gradient will be found using the gradient function, i.e. the derivative of this function here. Substituting x equals 1 in, that will deliver to you the gradient of the curve at this point, which is the gradient of that tangent. Let's pause this, go and see if you can find the equation of it, equation of this tangent, and then press play and see if we agree. Okay, so I'll go ahead now with the solution. I'm going to find y dash with my gradient function, 3x squared plus x, which equals 3 plus 1, which equals 4 at the point 1. Now what's the y coordinate? So this is 1, the y coordinate on the curve. Now don't go back in here, that's just for the gradient. We want to know the coordinate is on the curve. So 1 cubed is 1 plus a half times 1, so it's 1.5, or 3 over 2. Okay, so now I know that my gradient, the gradient of my tangent is 4, and this is the point here. So therefore, equation of tangent is y minus y1 equals m, which is 4, x minus x1, which is 1. Okay, that looks pretty good. Therefore, y minus 3 over 2 equals 4x minus 4. We could therefore say that y equals 4x. If I add 1.5 to both sides, that'll be minus 1.5. What's that? 2.5, or 5 over 2. 8 over 2 minus 8 over 2 plus 3 over 2 is minus 5 over 2. So y equals 4x minus 5 over 2 is the equation of the tangent at that point where x equals 1. Okay, the next example is find the equation of the normal, this time the normal, to the curve with equation y equals x cubed, so another cubic, doing something like this, at the point 1 minus 1. Now in this question, they've given us the y coordinate, so we've already got our x1, y1, so we've already got this and this. We just need to find this guy here, the gradient of the normal. Right, so if this is the point 1 minus 1 here, then the gradient of the normal will be that guy there. Right, and that's what we're after. We're after the equation of that. Now this is just a rough sketch, it could be anywhere, but I'm just giving you a little idea of what we're after. So, okay, again, if you think you can find the equation of the normal, remember the normal and the tangent have to be at right angles. They're perpendicular to each other. Go ahead and see if you can do that. That'll be brilliant if you can, and then just come back and replay my solution. Okay, so my solution to y dx, which is y dash, which is, it's all the same stuff. It's the gradient function. I'm deriving this 3x squared minus 4x. Okay, now that equals, I'm going to substitute 1 in there, because that's the point on the curve we're interested in. So that's 3 minus 4, which equals minus 1 at this point, 1 minus 1. So the gradient, now remember what we've done here, we found the gradient, the gradient function, we subbed in 1, so what have we found? The gradient of the tangent or the gradient of the normal? Right, hopefully you got that right. It's the gradient of the tangent we've got here. So therefore, really importantly, the gradient of the normal is equal to the negative reciprocal of this, which is 1. Or if you like, multiply to minus 1. So the gradient of normal is 1. So therefore, the equation of normal is, right, here we go, y minus y1, which is minus 1. So y minus minus 1, so y plus 1 equals, gradient of normal is 1. That's pretty easy. X minus x1, look at that, this is nice and simple. Therefore, y plus 1 is equal to x minus 1, or y is equal to x minus 2. And there's the equation of the normal. Okay, plenty of practice for you in exercise 20A, which is going to be your work for the next lesson. So I'll see you then.